So, have you ever stopped to wonder how a database actually stores your data? I mean, not the tables and rows we see, but what's really happening with the bytes on disk? Well, we're going to dive deep into the secret life of a database page and find out why a tiny number like 16 kilobytes is one of the most critical figures for database performance.
Because here's the thing. There's a really good chance your database is quietly wasting disk space, memory, and I/O cycles. And it's all happening because of choices you might be making in your application code without even realizing it. You just can't see it yet.
So where does this story begin? It starts with the absolute fundamental building block of a modern database like MySQL, the InnoDB page. See, databases don't read or write one row at a time. I mean, can you imagine how slow that would be? Instead, they work in much bigger chunks.
And that chunk is called a page. It's this fixed size container, and by default, it's 16 kilobytes. Every single thing that happens, from reading a row off the disk to caching it in memory, it all happens at the page level. You can think of it as the atom of your database world.
Okay, but you're probably wondering, why 16 kilobytes specifically? Why not 4, or maybe 64? Well, it turns out that 16K isn't some random number. It's a very carefully chosen sweet spot, a compromise that's engineered for maximum performance.
Yeah, this number is a strategic balancing act. It has to be big enough to work efficiently with modern hardware, both spinning hard drives and SSDs, but it also has to play nicely with the complex data structures that make your indexes so fast. All right, here's the crucial part. 16 kilobytes is big enough to grab a bunch of data from the disk in one shot, which is a massive win. But even more importantly, it has this huge positive impact on your indexes, specifically the B+Trees. Those are the magic data structures that keep your queries from taking forever. Now this is where it gets really interesting. Let's look at the real-world impact. If you use smaller 4 kilobyte pages, finding just one row in a table with a billion rows could take 4 separate trips to the disk. But with our 16 kilobyte pages, you can pack way more index pointers into each one. This makes the whole index tree wider, but also shallower. So now that same exact lookup only takes 3 disk reads. That's a 25% reduction in I/O from a single change. That is just massive at scale. So let's peek inside one of these 16 kilobyte containers. What's actually in there? It's not just a chaotic bucket of rows. Oh no, it's a highly structured, self-contained little mini file, and it's optimized for both data integrity and speed.
Every page has headers and trailers for things like metadata and checksums to prevent corruption. Then you have the space for your actual rows, the user records. But the secret sauce, the real magic, is the page directory. You can think of it like an index inside the index page. It lets the database do a super fast binary search to find a row on that page, instead of having to scan through every single one.
And this right here, this blows a lot of people's minds. It's a huge misconception. Your rows are not stored neatly in order of their primary key. Physically, they're just kind of thrown into a heap as they arrive. But logically, they're connected by pointers, creating a linked list that is sorted by the primary key. This is brilliant because it makes inserts incredibly fast. The database doesn't have to constantly reshuffle data.
Okay, so let's see how all this theory translates into real-world performance, or lack of performance. The way you design your tables, and especially your primary keys, has a direct, profound, and physical impact on these little 16 kilobyte pages. Let's start with database utopia, the absolute perfect scenario. You're using a primary key with auto-increment. This means every new key is sequential, and it's always greater than the last one. This is exactly what the database wants to see. Since every single insert is sequential, it just gets tacked on to the very end of the very last page in the index. It's like writing in a notebook. You fill up one page completely, then you just flip to the next clean one. The old pages stay packed 100% full. This is the dream, right? Densely packed data, almost zero wasted space, and lightning-fast writes. But now, let's talk about the nightmare scenario. It's a super common pattern that I see all the time, using random keys, like a UUID version 4, as your primary key. This one choice completely shatters that beautiful sequential order. So you've got this new row, its key is totally random. It doesn't belong at the end, it needs to be inserted somewhere in the middle of the index. But what happens when the page it needs to go on is already 100% full? Well, the database is forced to do one of its most expensive and painful operations. It's called a page split.
and it's awful. The database has to lock the page so nothing else can touch it, then it allocates a brand new empty page, and it painstakingly moves about half of the data from the old page to the new one. Then it has to rewire all the pointers. This is a stop the world event for that chunk of data, and it can even cause a chain reaction of more splits up the index tree. It's a brutal latency spike.
And the long-term damage? It's even worse. After that split, you're left with 2 pages that are now each only about 50% full. This is what we call fragmentation. You're now using twice the disk space and, more importantly, twice the precious memory cache to store the exact same amount of data. You are literally paying for RAM to cache empty air.
But random keys aren't the only way to get yourself into trouble at the page level. There's another common anti-pattern, and it's the indiscriminate use of select star, especially when you've got tables with large data types.
You see, when you use a text or blob column, InnoDB is actually really smart about it. It doesn't want to bloat the main data page with all that potentially huge data. So instead, it just stores a tiny 20-byte pointer on the main page, and the actual data gets stored on a whole separate chain of pages. This keeps your main index lean, mean, and fast. But the second you write select star, you're telling the database, hey, forget that clever plan. I want you to go follow every single one of those pointers and drag all of that off-page data back right now. This absolutely pollutes your memory cache, kicking out valuable index pages just to make room for a giant blog post that you probably didn't even need for that query.
So, what's the big takeaway from all of this? It's that your schema design choices, they're not just abstract concepts. They have direct physical consequences on how these 16 kilobyte pages get filled, managed, and perform. The action plan here is pretty crystal clear. For primary keys, stick with something sequential. Auto_increment is great. If you need UUIDs, use a modern time-ordered version like UUID v7. Just stay away from random keys. For large data, be a surgeon. Only select the specific columns you actually need, and for string data, right-size your columns. Don't use a text field for something that will only ever hold 50 characters.
All right, let's just boil this all down. Number 1, sequential keys are your best friend. They are your #1 defense against fragmentation. Number 2, just stop using select star on tables with large text or blob columns. It destroys your cache. 3, remember that every create table statement is a physical design decision. And finally, a low fill factor. All that empty space from page splits means you are paying for expensive hardware to cache nothing.
So, I'll leave you with this question. Now that you can kind of see the world through the eyes of a tiny 16 kilobyte page, what's the one single change you could make in your own schema, in your own application, today? Maybe it's fixing a primary key or refactoring a query. What can you do to make life just a little bit better for these hard-working pages?